Great. All right, so I noticed there's a question in the chat where there's an ask here. Can you discuss some packages compatible with Python that help us customize neural nets, especially if you want to work with RCNNs? So I'm not going to be the best person to ask about platforms. I can tell you that the answers that I'm going to give you are going to be the kind of standard marketing answers about packages like TensorFlow, for example, and a number of others, sort of very popular ones, either coming from the Facebook side of things or coming from the Google side of things. Me personally, I mean, I'm lucky if I get a chance to do any sort of implementation nowadays. And when I do, my instinct is to write it in Perl and MATLAB because that's where I was trained. And so I'm getting kind of like a little old to be a good authority on exactly the state of the art in implementation of these things. But I have a feeling that there are other people in this class who would be great authorities on that. So if you do have specific questions on, hey guys and gals, does anybody have a good recommendation for how to implement X in Python or Y in Python? That would be a great place to put in the discussion group, for example, or even possibly posting to the chat. And it's possible that somebody might be able to provide you an answer even during class within the chat, because I would just be spitballing. So I can tell you the fundamentals and can set you off in a research direction, but when it comes to implementation, usually I'm learning from my students. And so my students would be a much better authority on exactly how to do things than me. So, what's that phrase about those who can't do teach, so I'm not quite going that far to say I couldn't do, but it's been so long since I have done that I am way massively out of date. So I'm sorry, that's not a very satisfying answer, but I can guarantee you any answer I give you would not be satisfying. So any other questions or comments or anything to come up? Was I personally affected by a Zoom bombing? No, knock on wood. It's not an invitation, but I haven't been affected by a Zoom bombing. My wife had a minor, two minor incidents. One where a student didn't realize he was Zoom bombing her when he did, and that, but it wasn't that wasn't malicious. He just didn't realize he was using a feature of Zoom that affected everyone's screens, and so she just said, anybody who's doing, and I'm not going to tell you what that feature is, but he said, anybody who's doing that, please stop, and then they stopped and it went away. But I have a good friend who teaches Bio 181, a large freshman class, and they actually had someone display pornography behind them and drop their pants and things like that. And so that was sort of kicked off a lot of the scare about sort of Zoom bombing here. So I think in a lot of faculty's cases, the Zoom bombing is a function of their comfort when using the platform. And so, if people do these things, especially if you're logged in, there are ways to kick people out of the room, to prevent them from joining the room again, and all those sorts of things. And so it's kind of out of an abundance of caution. I haven't been directly affected by it in a negative way. I can anticipate ways in which it could happen, but I'm pretty comfortable that it actually helps me in organizational reasons. Like in other classes, I break my students out into breakout groups based on their project groups. And if I know their email addresses ahead of time and if they're logged into them, I can actually assign them to the breakout groups ahead of time, so I don't have to manually drag them over. So it's just more helpful to me if you log in with your authenticated ASU names. And that's kind of more a part of it, but I certainly know faculty have been negatively affected by it. It's a very small minority. Again, knock on wood. So any other questions? I mean, I hope things, in general, I went to grad school in the quarter system, and by this time, I was like super happy to be like at finals week and being done. And so the fact that we still have like another half semester or maybe less than a half a semester left to go, I know it's probably wearing thin on you. I know it's probably wearing thin on us too. So I can only imagine 15 weeks is hard enough in grad school, but then 15 weeks plus with this isolation and all of the uncertainty, So I just hope everybody's doing okay out there and keeping your mental health up somehow. So anything else anybody wants to cover before we go back into the neural networks, learning about how automation learns? All right. I actually put some of my ants behind me. So there's some an animation of a movie of a chain of weaver ants. So this is actually taken from a lab here at ASU. And so I have a student that works on weaver ants, and my wife actually collected these ants from Australia. And so if you look closely, you can see ants building a chain that allows them to move from one structure to another, and they just spontaneously form these things, and you can actually kind of milk them like cotton. So you can, because they're very visual, so you can put your fingers out there and kind of attract their attention, and then they'll start building a chain towards your fingers to investigate. So kind of interesting. So they're just kind of a cool thing to have around. And so I had a meeting today about swarms, and so it's just stuck from that meeting. All right. Okay, so last time we finished off talking about this different, I assume different, a sort of less traditional neural network framework for supervised learning called the reservoir machine, or reservoir computing, or a kind of more name brand version is the echo state networks. And so, and the key feature of reservoir machines, or I'll say the kind of branded version, echo state networks, and there are other branded versions, but this is just kind of the one that's the most popular, is that we are building complex neural networks, taking advantage of their high degrees of freedom for internal representation, but then we're leaving most of that alone and only training a very small portion of the neural network. And the fact that this works suggests that this back propagation process, where you're kind of training weights at the back of a network, maybe you don't actually have to go all the way back through the network. Maybe if you actually look at like how sensitive the network is, and sometimes those first layers kind of closest to the output are the ones that kind of get the biggest tweaking by back propagation in general. And so this kind of reservoir networks is kind of just saying, is just committing to this idea that, well, maybe actually we're just only going to train the last couple of layers and leave everything else just randomly connected. And maybe that'll be good enough, and then we don't have to train so much. So any type of supervised learning that you could do with a feed-forward network, in principle, you could do with a reservoir network. And because reservoir networks are recurrent neural networks, that also applies to time series applications. So just as a brief overview of that structure, the idea was you have your inputs go in, to, we'll call it just a randomly weighted recurrent neural network. And then those come out, and then you have a relatively simple, we can call this a decoding layer. That's fine. You can think of this as a kind of just an output layer. So you could think of this as, maybe a hidden layer and an output layer. So, so you could, we'll just call this a decoder, and we can call this maybe just like a hidden layer and an output layer. And this, and so the hidden layer is connected to a random subset of the reservoir. And this is the reservoir. So there's a good question. I was about to kind of mention this briefly here. There's a question about how do you initially randomize these weights, and isn't that really sensitive? So you certainly, so that's what it's kind of getting at here, is that the how you randomize these weights becomes the key question. So it's almost as if over here, then the decoder side of things, this really becomes the question is how to train the decoder, but it's a relatively simple decoder. So, you know, we can just use back propagation for that. And effectively, we treat this middle layer as a kind of, you know, quasi input. And so we view the reservoir as just a way of skewing our real inputs into this quasi input. And then you kind of forget that the reservoir exists. And this middle portion here ends up becoming the kind of inputs that we care about for the conventional task. So then that leaves, how do we create this little signal processing unit, this RNN here? And you could just randomly generate these weights. You could just say, okay, I'm gonna make all the weights go from -1 to 1. I'm just gonna draw them uniformly. But then there are a bunch of randomly weighted networks that's probably not going to work well for. And so if you look at the particular types of published reservoir machines out there, like the Echo State network, then you find that they have come up with heuristics that provide hyperparameters that constrain how you draw these random networks. And so there is a small set, so it's a coarse graining over this. So there's a small set of hyperparameters that tune the randomly drawn And so in the Echo State network, there's actually one of my students is in the class who's working with Echo State networks. And so he could rattle off, I think, the 3 hyperparameters that they work with. You know, you can imagine, like, effectively, you can think of the RNN is a random matrix where you can think of each weight as an entry of that matrix. And so you can then come up with hyperparameters on these randomly drawn matrices. And so, like, for example, spectral parameters. So you could say that I want to make sure this is a fully connected, that this matrix is like an adjacency matrix for the weights. And I want to make sure that there is a single connected component or something like that. So you could come up with a set of matrices that fit certain spectral parameters that you can define. And then once you've set those spectral parameters, then you can draw matrices that are constrained by those spectral parameters. And these hyperparameters have, for the most part, been kind of selected by some heuristic of the designers. So there's, they've just been kind of set based on things that kind of make sense by thinking this is a dynamical system. So maybe we want to make sure that this dynamical system that is in the reservoir is stable, is asymptotically stable. And we want to make sure that maybe it responds with certain timescale separation. So maybe it has some slow parts and maybe it has some fast parts. So you can imagine ways in which you shape these hyperparameters. And so even though there are millions of weights inside the reservoir, then there's actually only 2 or 3 hyperparameters that you set ahead of time and then have it draw those weights. And so this is a whole set of literature that if you're interested in, you know, I encourage you to take a look at. And I would start with Echo State networks and just sort of see what the Echo State network folks have decided on and see if they have good rationale for deciding on that. Because I think we could probably, you know, spend a week, you know, at least talking about this. So that's basically the idea between how to choose this randomization. So that then creates this new question of basically, you know, comes to how to train and then how to structure. So I guess I could say maybe that's the question over here, is how to structure the encoder is the question here, and how to train the decoder is the question here. And so because we've now created this new how to structure, it has simplified the question. This how to train has become less important. It becomes a much simpler problem. So it's your standard supervised learning, but we've hopefully allowed this to still do as much as a complex neural network, but have the training of a simpler neural network. That's kind of the point of reservoir machines. And we're going to go even farther now today as we get rid of the supervised part and we start talking about automation that sort of learns on its own or trains on its own. So as we move towards supervised learning, and then finally spiking neural networks and spike time dependent plasticity. So are there any questions about this reservoir structure, that it's just the evolution of these neural networks where we've actually gotten rid of some of the training and maybe actually gotten some benefits out of that? All right, so let's then see how we can further get rid of training. And so there is, I guess I should at least mention, so there's a question here. Reservoir machines are, I would say they are an alternative to RNN. So I mentioned this term, regularization. Maybe I'll put orange is not such a great color, so I'll choose this one. So there's this regularization term, which means a lot in a bunch of different contexts. But in the case of neural networks, it's a way of reducing the options in a neural network to improve the training process. And I would say that reservoir machines are an alternative structure, or are a regularized structure. They are a more specific and constrained topology for a recurrent neural network. So rather than building a recurrent neural network for this whole box here, and then in this recurrent neural network training everything, then the idea is, how do I come up with like a reduced type of recurrent neural network? The same way in my multi-layer perceptron, a simpler multi-layer perceptron was the convolutional neural net. So you can think of this as like a special case of an RNN, and it just has the weird feature that the recurrency is tied up in a box that you don't do any training on. So the recurrency is still there, but the training basically stays in this feed forward sense that you can do traditional backpropagation. You don't even have to do backpropagation through time on. So not a replacement, but a specialization to make the RNN simpler to use. And then I guess it's also, while I'm sitting here thinking about it, I might have written this last time, but for those of you that are not familiar with this already, I recommend, if you're interested in this idea of using randomness, I recommend looking into the field of compressed sensing, which is highly related to this. And so this idea of creating a random way to sort of slice up an input and then put it back together is compressed sensing. And so the idea in compressed sensing is, if I have an image, I could build a camera that takes a picture of the whole image. Or instead, and this is just one example, I could create a bunch of random filters that only look at random pixels in the image and then combine them all together into a sum. And that single sum goes into like a single pixel. And if I have a bunch of those pixels where each pixel is a different random sum of an image, then it's possible for me to use all of these sums together to reconstruct the original image. So even though I don't take a whole snapshot of the picture, by taking a bunch of different random snapshots, I still am able to capture all of the information in the picture. And I basically shifted spatial information into temporal information, which is very similar to where we're going to go when we get to spiking neural networks. And so compressed sensing is kind of does that a little bit more explicitly. And there's a little bit of an implicit connection in these RNNs, where we are again taking random slices of the input, possibly across time, and putting them together in funny ways. And then hopefully those funny ways extract useful information about the inputs that don't require us to actually have a feed-forward network keeping track of every single aspect of the input. So that's kind of the hand-wavy version of what's going on with these RNNs. All right, so what I want to pivot then to is from supervised learning to something in between supervised and unsupervised learning, where we're ultimately going, and to reinforcement learning. And so this is almost an aside, but I just want to bring it up so that it's out there and we've covered it. Reinforcement learning provides autonomous systems, robots, or even systems that are crawling over abstract spaces like images or data in a database. That these are methods for exploring an environment that that as you're exploring, you're experiencing reward from your actions. And so they are based on discovering actions that maximize reward. And so there are a lot of strong connections to, for example, Markov decision processes. Which, if you're not familiar with MDPs, an MDP is basically just a Markov chain where you are actually modeling action. So as you enter a state, then you have a rule which tells you which state you're more likely to go into. And so your goal is to design rules which allow you to move through this Markov chain in a way that somehow maximizes your accumulated reward. And so a Markov decision process, reinforcement learning can be modeled as a Markov decision process. And so there are a bunch of different mechanisms that have been used over time to implement reinforcement learning. And the reason I'm sort of putting this in between supervised and unsupervised, supervised learning is kind of like, here's a data set, and I've labeled the data set. I want you to learn the relationship between the data and the labels so that if I later give you a data set, you'll be able to tell me what the right label is. And that's supervised learning. And so after the training is done, then we've got a trained expert, and we don't ever have it retrain itself. So it just sits there as being, it just encodes information from all of that training data and then applies it. In this case, we're actually unleashing something that needs to discover the right thing to do as it's actually doing the task. So there are a bunch of techniques, and so the old school technique that you still see today is so I'll say this is common and old, is called Q learning, and where Q is short for quality, so learning of quality, Q learning. And so Q is a running estimate, and we're going to get back to neural networks in just a second, of the reward for any pair of state and action. So I mentioned that like a Markov decision process, you can think of like a Markov chain that has states that you move between, but you actually can control the probabilities of moving from some states to some other states. And so you have a state and an action that you can make. And so Q learning is sort of learning how to generate those probabilities as you move through this Markov chain that's kind of governing your motions. And so this, I'll just abbreviate this as QSA. This is like a map. This is, you know, you think of it as an objective function that you have to learn over time. So it's kind of now we're getting back to something that looks like a genetic algorithm where I'm trying to maximize an objective. I have the ability to evaluate the objective at any particular point, but I do not know the shape of that objective. I have to actually discover the shape of the objective as I am moving through the action space. So this function QSA is discovered over time. And I apologize, this is going to be a review for some of you. Just again, want to just kind of, you know, give us a conceptual framework that we've got kind of in mind here. And so the problem in approximating this function QSA is that it can be very large and ugly if the number of actions and the number of states are very large. And so, thanks for that positive feedback, yeah. And so this QSA here you can say, well, how the heck am I going to approximate this? Well, one way to do that is to actually train a neural network to approximate the QSA. So one option here is to say for large state action spaces, we can use an ANN can approximate Q. So the inputs, so you can see now there's a tie between reinforcement learning and supervised learning, because now that you've got these rewards coming back in, you can actually use that in a kind of online training process where you've got a neural network that is gradually reshaping itself. So what is being enforced is the question here. And so we can imagine that our agent, our actor, is in a particular state and takes a particular action. So we're in a particular state and we take a particular action, and that action may bring us to a particular next state, I'll say state prime, but it will have some reward or penalty. So I do not know, and so this is the QSA. And so for the particular state S that I'm in and the particular action A that I take, I do not know what this reward is going to be. And so as I'm popping around the different states, so these states could be positions. So I'm at this particular position and I move left. Well, it turns out that if I stand next to the volcano and move left, I walk right into the lava. So as I walk into the lava, then I need to learn, that was a bad thing to do. So when you're standing next to the lava, don't go left into the lava. So that's bad. So I can learn that. So that becomes part of my training set for my internal neural network. So if I ever come back to that state, standing next to the lava, then maybe I try going right instead. And now when I go right, I find out, that actually maybe it actually gets a little cooler. So maybe I now am rewarded for that. And so that goes into my training set. So my training set becomes for this state, this position, and this action, left, right, up, down, etc., then I get an evaluation of whether that was a good thing to do or a bad thing to do. And that is what I'm trying to encode inside the neural network, so that as this neural network gradually builds up a map of the space, then I can then use that neural network to guide my decision making as I move forward. All right, so there is so this question here of so this question of what are the APOCs for this this ANN, and so that's kind of what I'm sort of getting into here. And so so I'll just add that briefly here. Before I handle these two, let me just get the rest of this page down, and then I can handle those. And so the ANN is not being trained by RL. Well, okay, so this is kind of a strong statement. It's being trained in the RL process, but it's not, we're not using RL as a way to train an ANN. We're using an ANN inside. So, so the ANN is not being trained by an RL process. So in other words, I'm not saying RL is not an alternative to backpropagation. We could say, but the ANN is being used inside the RL. But of course, I still need the RL to interface with training of the neural network. And it turns out that there are many ways to do online ANN reinforcement. So you can think of this as sort of back propagation over every action. You can also use genetic algorithms to adjust ANN structure. And weights based on the reinforcement. And so I don't, because this is just sort of an aside, I don't want to get into this as a, and we could go into a lot of detail here. So there's much more to say here. But I just want to give you this idea that you, so that somebody asked, is a genetic algorithm modeled in the architecture similar to the NEAT algorithm? NEAT, the neuroevolution of augmenting technologies, is one way to apply genetic algorithms to the design of neural networks. And so the reason I'm just bringing both of these things up is you can imagine that there are back propagation ways of doing this. So you can try to say, how do I adapt back propagation where every time I get a reward, I kind of treat that as an error that sort of ripples backwards through my neural network and adjusts the weights in a way that kind of causes them to move to better to capture this reward structure. But you can imagine getting rid of back propagation entirely and then going with something like a GA or like NEAT that is able to actually use these rewards in a kind of genetic algorithm way where with every reward, it adjusts maybe different topologies. So it might be that during a training period of your RL, you've actually got multiple neural networks that you're keeping around, like populations of neural networks, and you gradually converge on one, and then you reach some sort of exploration-exploitation trade-off where you say, okay, I'm done training, and I am just going to now move forward, assuming that my neural network is in good shape. And then if you ever get make a really bad action that you didn't expect from your neural network, maybe you then you reset the training algorithm. So you could imagine, for example, I'll say example, adaptive resetting. So you switch from learning to using mode, but then if your using mode predicts a reward that's very different than the reward you actually get, you go back into learning mode. So this is a very rich set of literature on how you use neural networks to inside reinforcement learning, and I'm just trying to give you a flavor of it. So let me go back through the questions that I see here. So that my attempt to fill out this was in part an attempt to answer Jameson's question, in that there are a lot of answers to this, and you could imagine a lot of different solutions to this problem. Then you say, what is the input of the ANN here? Swastik's question. So the ANN's input is the state action pair, and the output of the ANN, well, I kind of say, what do we mean by input? So what I'm saying here is that I'll write this in a different color, the QSA is what is being approximated by the ANN. So it's like the ANN takes the state action pair as an input, and it produces Q as an output. But our goal is to then train the ANN so that this is a good approximation. So during the training process, you can view the reward as kind of an input to the training process of that tiny ANN in the middle. But overall, once you're done training it, then the input to the ANN is the current state and action. And you can think, or you could say the current state and then all, impossible actions. And then the output is the kind of quality across all those possible actions. So then we use the ANN in order to decide what the next action we take is in this trained reinforcement learning algorithm. Can I give an example here? Not sure how the components are fitting together, like the input to the ANN, the output, and where does the output fit? And how does the online part work? Does it mean the ANN is retrained and Q is modified again? You can imagine Q is fixed in the environment. There is just some quality that we don't know. And so the ANN is effectively a memory that helps us remember all of the cues that we have experienced through our history moving through the space. And so I need to learn that there is an edge at the end of the table. And the only way I can learn that is if I get to the edge of the table. So I see an example here. Deep Q learning is one of the examples of mixing RL and ANN. So excellent point. So we can put in here that deep Q learning is another, more info. So the deep here in this deep Q learning idea is this idea that I have a complicated function Q that I'm trying to approximate with a neural network. And so if I want to use deep learning to approximate this function, then maybe I want to use deep Q learning. So the idea here is that the ANN is just an approximator of Q. If I had Q, I could make decisions in this space. Q tells me how my actions relate to the rest of the world in terms of positive reward and negative and punishment. And so I don't know that. So as I move around, I have to remember it. My memory is the ANN. And Ankit, does that answer your question? Swastik, you said, and as the RL keeps iterating, the Q values keep changing until saturation. The approximated Q inside the ANN keeps changing. So if I guess I could put a little tilde or something over this Q. And so my ANN is an approximation of the real Q. And so you can think of this as, learning through playing a game, right? You can think of an ANN is a model of the learner's brain. And as the learner is playing a game, they are getting reinforced for certain actions. So they don't know the rules of the game. So you could view this as an approximation of the rules of a game. And so if you didn't know how to play checkers and you sit down in front of checkers and then you start moving and you see your score, then as you see your, well, I guess checkers is around a score, but if you think of a game, a board game you could play where you could easily measure your score, then as you saw moves cause your score to go up or down, then gradually using the differential changes in your score, you might be able to encode the entire game into the neural network. And then once it's encoded in the neural network, then you could use the neural network to decide on your next move in the game. So, so this idea here is that I'm using a neural network to learn the rules of the game. The optimal policy for state Q will be the argmax over the actions. Yes, you can think of that as you're trying to learn the optimization objective, and once you learn Q, then you can have a decision-making algorithm choose the action based on your learned Q. And then okay, good question. So where do we get the labels? The labels come from the robot that's moving around. So that's why this is in between supervised and unsupervised learning. In supervised learning, a human gives you all the data and the labels ahead of time. And reinforcement learning, you tell the robot, I'm not going to tell you what the objective is. I don't actually know what's a good action or a bad action exactly, but I know that there's some actions are going to be better than others. And I know you, robot, as you move around the world, you are going to immediately be able to discover whether you've made a good choice or a bad choice. So I'm going to sit you down here and press go and just let you start moving around the world. And so initially the robot moves randomly around the world and it keeps getting positive reinforcement and negative reinforcement. And that reinforcement that the robot receives from moving around the world become the labels. And so we are looking for, so if I go to this next page, we can say that Q learning, or even deep Q learning. So Q learning in general need not have a neural network, but we can use a neural network to approximate Q. So that's this intersection with neural networks. And so the idea here is that I am approximating Q by a neural network. And so labels come from reinforcement as I'm going to use the word randomly, but it's kind of a bad use of word here, move around state space. And I could even say state action space. And so I don't get labels ahead of time, I discover the labels. And so you can think of the inputs as state action pairs. You can think of the labels as discovered rewards. So then together, you're learning the reward function QSA. All right, so guys, so Kevin checked that one off. So I see, so the robot moves around the exploration, and once we get through enough samples, an approximation for Q, you can go into exploitation. Yes, Ankit, that's a good way to view that, is that you can view this as two phases. You can view it as kind of an exploration phase where you're learning Q, and then you can view that as shifting then to an exploitation phase where you're using Q, and you could even imagine potentially shifting back as necessary, going back and forth. Yes, yes. So it looks like we're getting all, I'm liking the comments here. These are all matching what I'm hoping to communicate here. So any other questions about this Q learning? Because I want to move on to just the unsupervised, general unsupervised learning, but I wanted to throw that out there as a way where you can take supervised learning and use it inside something that interacts with your environment. And so it's sort of a weird combination where we don't know the labels, but we can allow an automated system like a robot to discover the labels and then use supervised learning inside a kind of unsupervised learner. So it's almost like the learner is getting its labels from the environment instead of from you. And so there's a question here, does the way Google, so this is a good question about these games. So the question is, does the Google Go game fall into this category? And so the way that you train deep learners to play a complicated game like Go, may not actually involve real-time learning. So it may involve, during the learning process, you may actually have a kind of label generation that makes it kind of feel like reinforcement. So there can be reinforcement learning involved in this. And so it gets a little muddy as to what's what, especially because like eventually once you get to this exploitation phase, it's hard to sort of separate the neural network from the thing using the neural network. So yes, you could kind of say that there is one way you can train a neural network to play a game is through reinforcement learning. And you make use of a neural network to learn, say, the Q value. And so the Q function, this reward function, you can learn using the neural networks. I don't want to say that that's the only way you can learn to play a game. I could take a database of actions that people made in games and just use that in a plain old supervised learning sense. The kind of RL is when you actually kind of allow the automaton to discover different actions it can make and then learn from improvising. So if there's improvisation and reinforcement involved, then we can call that reinforcement learning. And Q learning is one way to implement reinforcement learning. And deep Q learning, or just learning Q learning that makes use of a neural network to approximate the Q function, is a further specialization of Q learning. When Q learning first came out, this is almost like good old-fashioned AI. It wasn't necessarily involved with neural networks. The addition to neural networks to Q learning happened after. I see some questions here. Are the Q learning equations something similar to what an ANN is doing? If I recall correctly, the Q update was based on a least squares calculation. Absolutely. So I would say that like least squares is another one of these tools. So like the idea of least squares or loss functions, I would say that these are just general tools of optimization. And so it's sort of no surprise that in doing supervised learning of a neural network, that people have turned to these tools and they've said, okay, we need to find some way to guide the movement of these weights. Well, why don't we come up with a loss function? And if we come up with a loss function, what's a good loss function to come up with? Least squares, why not? So there are a lot of good reasons to use least squares. So it's not surprising that any time that you're doing something that looks like an optimizer, there may be an opportunity for things like least squares to come into play. So, so I would say that the apparently superficial relationship between backpropagation and Q learning is not accidental, but it also is not, I wouldn't read too much into it, so much as they both are making use of tools that were already available from the optimization community. And so that's the reason why they're kind of in common. They aren't necessarily in common because like one is a version of the other. It's just like they're both simple versions of something that was already out there. Can I explain this in a flow chart? It might be helpful to visually see a flow chart of this. And so I guess I could try. If you were to sort of think about the flow of these things, then I guess we have a robot, or you take an action, and from there there's receive a reward, and from that receiving the reward, then you can kind of view that as update ANN. And so here you can view the input as the state action and the output or the label as the reward. And then from there, you can imagine kind of going back and then taking another action again. And I guess maybe I could have involved, a check. So I could go back and maybe add a little check here to say, if we've converged. And if not, then we continue. This is kind of the You can view this as the exploration or learning loop. And then if we have converged, then we can view this as the kind of exploitation. And from here, then we can have, another kind of subroutine that, chooses action based on A and N. So I'm not sure if that helps, but you can view this kind of reinforcement learning loop as progressively getting information to make your neural network closer and closer to Q. And eventually, once your neural network kind of settles down, so you have some convergence criteria, just like in the meta-heuristics that we learned about, then you go into an exploration mode where you can then use that neural network to guide your next step. And then how do we judge convergence? There's lots of different ways to convergence is always a hard thing, but you could say, well, maybe it's so many actions I go through here. Maybe it's whether or not if I were to look at all of my weights as a vector, then maybe I can measure the distance between my previous vector and my previous step and this vector, and maybe those settle down over time. Maybe I see how many times I've landed on a particular state action. Maybe I look at how well my current neural network predicts the reward that I'm getting, because it might be that I manage to interpolate or extrapolate and I do pretty well. So if during this loop, I end up not learning anything because my predicted label matches the label I've discovered, then maybe it's time for me to just start making decisions. So, right, the Q values would be this, yeah. Mm-hmm. So that's reinforcement learning and Q learning in a nutshell. So, so let's see where we can go from there. So this kind of, I was going to say, well, what if we now cut off reinforcement totally? Then is there a way for us to still learn things? So we're not actually going to have any reward function. We're just going to allow the neural networks to figure things out on their own. I see a question here. Isn't this all under the assumption that we know all the actions are possible in the space? What if we don't know all possible actions? So of course, this is a much more complicated topic. And so I was sort of putting under the rug this idea that for every state, we kind of know all of the actions that are feasible. And so I was just kind of assuming that that was one of the things kind of going into this problem, is that for every state, we have a set of actions. We just don't know the rewards for those actions. And as we move from one state to another, we have a different set of actions. So, and this a question about observability, then you can add those wrinkles into it too. What if the reward function that I get has noise? And what if the reward function that I get is somehow degenerate in that I can't actually manage to discover the entire state action space based on how I'm getting these rewards? So, there's a lot of cool directions you can go into, and like, what is it possible for you to learn on your own? And at what point do you need an oracle to give you information in order for you to make progress? So that's all kind of in the kind of reinforcement learning literature and related. So the Markov decision process literature, for example, or even the observer literature and the estimator literature. So there's a much wider literature on how automated systems take inferences from awards that they measure from their actions. And so, and also it doesn't have to be a deterministic automaton. This can be each one of these actions, you can be reshaping the probability that you take actions. So you might be maximizing over your Q function when you choose your action, or maybe you are weighting your probabilities to make an action based on the relative rewards that you get. So you can add all sorts of complications to this. Okay. All right, but let's forget about rewards for a while and go into the realm of things where we need to solve problems where we don't know what the reward function will be, and we just want to let the neural network do something interesting. And then hopefully that thing that's interesting will be useful to us as the human benefactors of that neural network. And so we now are shifting to unsupervised learning. And this will allow me to introduce spiking neural networks as well. So how do we learn without reinforcement? And so the idea here is that we are going to input is provided, but no desired output is specified. And from a desired output, through a loss function, we generate a reward. So implicitly, what I'm also, an alternative way to say that is to say no reward or punishment, if you like, is provided. We are just providing data, and that's it. There's no just input. And so what can we do with that? And so, as an example, I might provide some data on axes x1 and x2, and there's just a bunch of data points. And when you look at that, I'm guessing that most of you immediately see the number 4. Like you might see there's other dots there. You may not have counted how many dots that I drew there, but you immediately see the number 4. And you could say, well, how the heck did I see the number 4? Well, you saw 4 clusters. Well, what the heck's a cluster? Well, you could say, well, Ted, a cluster is, this is a cluster, and this is a cluster, and this is a cluster, and that's a cluster. And I will just label these clusters, cluster 1 and cluster 2 and cluster 3 and cluster 4. And then you say, I see 4 clusters. That's how I saw the number 4. But why did I decide that this was a cluster? And then you say, well, it just seems like those points are more similar to these other points, et cetera, et cetera. And you can see, as you go down this rabbit hole, we see that when we look at these points and we immediately see the number 4, our brains, without any reward, without me telling you what I wanted you to see, immediately reasoned about this data, structured it, and then represented it as an interesting coarse-grained quantity. And that's kind of the essence of unsupervised learning. And one of the kind of key problems of unsupervised learning is the clustering problem, where you're effectively coming up with labels on your own for data based on how those data relate to each other, not how they relate to some external label. So you could view that as kind of autonomous labeling of anonymous data. I'm not quite sure I like that phrase. I just kind of came up with that. The term anonymous is a little loaded, but, and then you can say, well, why would that possibly be useful? Well, you could imagine special cases of that. For example, if you had a data set that represented, I don't know, how long people visited a web page, or how long people were clicking, how long people clicked on a particular area of a web page, or you've got these data on people's behavior. So you might have some behavioral data, and you notice that generally most of your data falls into some type of group, but occasionally you get a point that's out here. And I'll answer that question here in a second. And so what you end up forming is an identification of 2 clusters, where this is sort of the normal behavior, and this is an anomaly. And so, you walk into a retail store, which I'm sure some of you will eventually do once, in the future, hopefully not long from now. And if you behave in a weird way, then somebody who works at that store comes up to you and says, oh, can I help you with something? And so that is an identification that they have done a clustering problem. They have sort of said that you're not behaving like everybody else in the store, and so maybe you need extra help, or maybe I need to investigate that you're participating like a customer should participate. Whereas all the other customers, I don't actually know what they're doing, but they're kind of doing the same thing. So there's a question here. So it's up to us to observe and evaluate the ultimate outcome after the inputs are fed. Well, so we're saying that the neural network comes up with its idea of how a neural network comes up with some interesting representation of our data, and then we have to figure out what that representation means. But the fact that the neural network kind of becomes an object, so in supervised learning, we impose our own biases on the neural network. So we say that this is a good outcome, this is a bad outcome, and then so the neural network reflects our psychology, or whatever was used to label. Here, we're taking all that out, and we're sort of allowing the neural network to take an objective shot at the data. And then this objective shot at the data, then it sort of says, okay, here's how the neural network broke things out. And then so from there, you can say, that's an interesting way to slice these things up. I now have an objective measurement of these clusters. And so you can't argue, like, before, if I were to manually draw this, you could say, oh, your human biases are affecting your clustering. And now I've gotten rid of the biases and I've let an objective thing to do that. And then I can then also then put that in a application like this one, where maybe I need to do, for situational awareness, for example. So that's kind of a key area. Or SA. So I might want an autonomous system to be able to detect when things are wrong or weird. And so I don't know what good behavior is, but I have a bunch of behavior that's going on. And I then, and there might be bad behaviors that are going on inside those good behaviors, I don't know. So rather than me specifically giving a template for bad behavior and a template for good behavior, I just give it all behaviors, and then I allow it to kind of find the outliers. And I might not, this might be such a high dimensional space that I can't simply plot a histogram and then say, this tail behavior is an outlier. And so in this case, I'm saying, well, how do I compress all of these dimensions down into a manageable thing and still be able to find these outliers? And that's one of the key things that I depend on this unsupervised learning to do, is to effectively detect clusters and detect outliers. And so without me giving it any training data, just sort of be able to divide up the data in a useful way. And in my retail store example, I promise was, I don't know, a movie I saw or something. But so this, I hope, will remind you of things like the artificial immune system. Where in that meta-heuristic, we were trying to build a system that is able to sort of build a template for weird behavior, or use a template for good behavior and assume everything else is bad. So there's these like clonal selection and negative selection, and kind of two ways they're doing it. And this all kind of fits into this computational creativity, where again, we get rid of the human biases and we just allow the computer to kind of do something interesting. Now, we can also use these methods to enhance supervised learning by, so there's, I don't want to go too much down a rabbit hole because this is a kind of a hot area, but you can, in this sort of area of computational creativity, so if I was to sort of put that as a heading, then a tool that I'm sure that many of you have heard about, and especially in terms of reinforcement learning, but also just in other types of creative applications, are the so-called GANs, or generative adversarial networks. We're just going to abbreviate that as nets, where in this case, you have two networks that can interface with each other, where you can kind of think of one of them as generating data, and the other one is generating classifications of data. So for example, if I really want this to detect anomalies, I can then also train this neural network to generate anomalies. And I can actually provide, so you can imagine sort of, there actually being loss functions that are guiding a supervised process on both individual network, but because I've tied them together, I've effectively moved the human and all data out of the loop, so that these two can fight each other and they'll both hopefully get better. And so as this network gets better at detecting anomalies, then this network will get better at generating anomalies. And so this allows this computational creativity to iterate even farther than it would if I just gave it a sole data set. So, so this is one way to kind of amplify this creativity, is to actually provide a data generator that you don't know what the data generator is supposed to look like either. And so you actually treat that as a design problem as well. And so gradually these two things over time. So you can imagine that one of these things is trying to come up with identifying patterns in a player's moves in chess, where another one is actually trying to then come up with ways to disguise their intentions in their chess moves. And so you end up getting these two things iterating over time. And so I don't want to go into great detail here, but I would also cluster, so to speak, GANs as another type of unsupervised learning. So it's an unsupervised learning because we are closing the loop with another ANN. And so those two ANNs together is like a giant unsupervised system that's rattling along, hopefully getting better and better at some task. And yeah, you have to initialize these. I mean, if you're to think, these GANs, if you cut a GAN in half, then this may just be a standard supervised learning, which in that case, you initialize the weights randomly, et cetera, et cetera. And so you would imagine, initializing these two, and maybe you initialize them with some, you train this one based on a task, and it becomes pretty good at it. And you train this one on the complementary task, and it becomes pretty good at it. And then now that they've both been pre-trained, like sort of a warm start, then you can put them together and see if you can make them better and better. So that's one way you can generate these GANs. So if you've heard of these GANs, it's kind of a brief intro to where they're all about. So it is a way of closing loops around supervised learning to provide unsupervised learning. All right. The only other note I want to make about this clustering before I kind of go to more kind of generalization here is that for, say, anomaly detection is more complicated in time. And what I mean by that is at a particular instant, if you were to just take some data at an instant, then that data may not show evidence of any anomaly, but it might actually be the pattern of data over time. And so this may require a dynamic representational abilities. In other words, things like RNNs. So, so you may might require feed-forward networks, but you have to feed it in a history. Yeah, I can say, or you know, even I'll say feed multi-layer perceptrons with input history. So it's not quite as simple as I give it a snapshot and it finds an anomaly, because anomalies can happen in time as well. So, but this is sort of an interesting application area, anomaly detection. How do I, in an autonomous way, be able to detect when something is weird without kind of knowing what weird is ahead of time? All right. So that's kind of the first application of this unsupervised learning. Where we're going to go from here in the back half of this lecture, and then I think that's the end of this unit before, and then the next unit is going to go into interacting particle systems and cellular automata. So there's probably one more lecture in this unit. And where we're going with that is in multidimensional scaling. So how does unsupervised learning relate to the problem of compressing dimensionality? And then from there, mechanisms for online unsupervised learning, like Hebbian learning, which we can implement in a traditional neural network, or spike time dependent plasticity, which we can implement in a more nature-inspired spiking neural network. And so that's kind of where we'll end things at the spiking neural networks of this unit. So it's 4:18 now though, so I feel like this is a good place to pause. So are there any additional questions about this stuff? Or comments about how things are going in your semester or your classes? All right. Otherwise, I don't have anything else to offer for today. Like I said, I'll stop there and we'll pick up whenever the heck the next day is, Monday. And so if there's, I can hang around for a few minutes. And for anybody else who does have any questions, I'm going to stop the recording. At 4:30, I have another appointment, but next office hours are Monday. I don't have a midterm update. If the midterm goes so long without me putting it out there, it's just going to become the final, and I'm going to find another way to give you guys a grade for the midterm. You know, that might mean dropping the midterm, but I want to make sure I do it delicately because I don't want to make your grades more fragile. So I've kept all that in mind. I know that I've been really tardy about that. I am not going to launch a midterm on you and say, okay, midterm's released on Monday, it's due on Wednesday. I'm not going to do anything like that. But I want to make sure that I at least put checks in the box of all the grades that are on the syllabus. And so if I have a way to synthesize a midterm from other grades or something like that, I'll do that. But if worse comes worst, midterm will become a final and something else will go in the midterm slot. And then, oh, project proposals, thanks, Emily. As a reminder, your project proposals are due this weekend. Those of you who've turned them in, I've graded. So I'm still working on that first homework. It takes me longer to grade, but your project proposals, I have a quick turnaround on those. And so those, the ones that have been turned in already have been graded. If you haven't turned them in, just looking for 2 paragraphs, really. I've tried to clarify it on the assignment. If you go back to that assignment, first paragraph kind of tells me in words how the algorithm works. Second paragraph tells me how your demo works and how your demo will highlight aspects of the algorithm and how it kind of differs from other ways to solve the problem. Any other questions or comments? All right, thanks for your patience with me this semester, and you've given me some good feedback over email. I'm doing my best, and so that's good. Okay, so I see a technical question here. So what I'm going to do is, it's 4:21, so if anybody wants to head out, feel free to head out. I will hang around here till 4:30 answering any additional questions. I'll stop the recording at 4:30 or whenever the questions are over, and they'll be posted for anybody who needs to leave but wants to hear the questions. So there's a question here, unsupervised learning and its dimensionality regression. So I see. So if we can have some points behave in certain ways and put together by the unsupervised learning outcome, then we can replace them with a label and reduce dimensions. Is that an idea? And yeah, you can actually view it that way. And in fact, you could view clustering itself as kind of a type of dimensionality reduction, where you've taken this multidimensional space and you somehow encoded these points in a way that captures that they're different while losing some of the aspects of their differences. And we can more formalize that for dimensionality reduction, where you can say, neural network, here is a multidimensional space. I'd like you to generate points in a finite dimensional space, but I would like you to do it in a way that maintains distances between these points. And so there's ways in which the neural network can do that. And so we'll talk about some of those ways. And they basically involve kind of like this generative artificial network. An easy way to do this is to actually take something from supervised learning and wrap a feedback around it to turn it into unsupervised learning. And the latent variables will become the dimensionality reduced version of the data. But we will cover all of that on Monday. All right, any other questions from anybody who's remains? Okay. Well, thanks as always for all your participation today, and I will see you on Monday. I hope you have a good weekend. If you have any questions about the final project proposal, send me a note, but don't overthink it. It's just 2 paragraphs.